Hi, everyone. We're continuing with our graph of y equals sine of theta, and we have the fundamental cycle over here, which we discussed earlier. In fact, we can actually graph this thing on Desmos, y equals sine of theta. By the way, in order to get these quadrantal angles here on the horizontal axis, you can go to the wrench here. I made the step size pi over 2 here, and you might want to resize the y-axis as well, the y scale. But I rescaled the x-axis, and I made the step size pi over 2 so that we have quadrantal angles as the labels here. When you start off Desmos, that usually is not the case. Also, I'm in projector mode, so you can see the coordinates better. Okay, now the fundamental cycle goes from 0 to 2 pi. Okay, annotate. The fundamental cycle goes from 0 to 2 pi. Oops. So this piece over here, this piece over here. All right. Now, here's the fundamental cycle. It's the good morning graph from theta equals 0 to theta equals 2 pi. The range, by the way, goes from -1 to 1. Those are all the y coordinates we pick up. Those are all the possible sine values we can pick up. Now, notice that if we keep zooming out, we see that this graph goes on and on and on. The domain is all real numbers. You can plug in any real value for theta, and you're good. Domain of this is all real numbers. So this fundamental cycle is repeated like a piece of wallpaper, forever and ever to the right and forever and ever to the left. Okay, so over here, here's our fundamental cycle over here, but then it keeps getting copied over here from 2 pi to 4 pi, from 4 pi to 6 pi, and so forth. Also back here, from -2 pi to 0. We have infinitely many cycles, and this graph is periodic. The function is periodic because we have this finite piece of wallpaper that gets repeated infinitely many times to the right and to the left, and that forms the entire graph. This changes in cycles. The period is 2 pi. That's the width of a fundamental cycle. The period here is 2 pi. Period equals 2 pi. The period is the width of such a cycle. A cycle is the smallest, thinnest piece of wallpaper that you need to have in order to have the property that when you repeat it forever to the right and to the left, you do get the overall graph. We need all of this cycle over here, but no more. This is enough for us to repeat. Over here, red cycle, blue cycle, purple cycle over here. We have 3 cycles over here, each of with 2 pi radians. And notice something else. This graph is symmetric about the origin. If you take this sine wave and you rotate it 180 degrees about the origin, you get the same graph. The sine function is odd. Sound familiar? The even-odd identities. The sine function is odd. The graph is symmetric about the origin. The graph is symmetric about the origin, which is the typical case with odd functions. So we have now the entire graph of y equals sine of theta. We have infinitely many cycles. This one over here, this good morning graph, is the fundamental cycle. Period is 2 pi. It's the width of a cycle, the thinnest piece of wallpaper that is sufficient. Okay, so that's the graph of y equals sine of theta. What about the graph of y equals cosine of theta? Cosine of theta corresponds to the x-coordinate of this intersection point. Let's trace it out. Again, I'm going to go to a frame. All right, so this is the fundamental cycle for y equals cosine of theta. Again, we have our candy bar, our Kit Kat bar here. 3 line segments here, 5 line segments vertically. All right. We're going from theta equals 0 to theta equals 2 pi. We're taking a tour around the unit circle here. And we're tracing the behavior now of the x-coordinate, the cosine value of theta. All right. When theta equals 0, the cosine value is the x-coordinate. What's the x-coordinate of this point? It is 1. Cosine of 0 is 1. When theta is 0, cosine is 1. We get a max point. Remember, I refer to the origin, or the point that corresponds to the origin, as the pivot, the pivotal point of the frame. For the basic sine cycle, the graph contained the pivot. But for the fundamental cosine cycle, that does not contain the pivot. It contains this maximum point up at 0, 1. Now, as we go from theta equals 0 to theta equals pi over 2, the x-coordinate, the cosine value, does what? It decreases from 1 down to 0. Cosine of pi over 2 is 0. Remember COS? COS, that trick. Cosine of pi over 2 is 0. The cosine function decreases in quadrant 1. Cosine at pi over 2 is 0. And we get this theta intercept. In general, I'm going to call this an inflection point, a point where the graph changes concavity, in this case from concave down to concave up. Because later on, when we translate this graph, this may no longer be an intercept. It's still an inflection point. All right, as we go from theta equals pi over 2 to theta equals pi, what's happening to the x-coordinate, the cosine value? It's going down from 0 to negative 1. Cosine value, cosine value goes from 0 down to negative 1. Cosine of pi is negative 1. The x-coordinate here is negative 1. All right. Going from theta equals pi to theta equals 3 pi over 2 through quadrant 3, the x-coordinate, the cosine value, increases from negative 1 back to 0. So the y-coordinate here on this graph goes from negative 1 up to 0. Don't confuse coordinates here with coordinates there. Cosine values here correspond to y-coordinates here, not x-coordinates. All right. And then, as theta goes from 3 pi over 2 up to 2 pi, back to this east point, the x-coordinate, the cosine value, goes from 0 back up to 1. Over here, 0 back up to 1, a max point. So once again, just like for sine, we're picking up 5 key points. This time, we're picking up 2 maximum points, 2 inflection points. There's an inflection point over here, and 1 midpoint. I call this a valley graph, or maybe a curvy V graph. This is the fundamental cycle for y equals cosine of theta. Curvy V or valley. And don't forget to label the coordinate axes at the end. Theta over here at the right end. And remember, you put this at the positive end. Don't put theta over here. Put the label at the positive end. People forget that. And then we put y, or f of theta, up on top, not on the bottom. Remember, you put it at the positive end of each axis, the label. All right. Once again, the period is 2 pi. So here's one cycle in red from 0 to 2 pi, another cycle in blue, over here another cycle in purple. On Desmos, let's graph y equals cosine of theta. Okay, starting at 0, 1, here's a curvy V going to 2 pi, 1. That's a fundamental cycle. But then we repeat this. So we have 0 to 2 pi, 2 pi to 4 pi, 4 pi to 6 pi, also backwards. Negative 2 pi to 0, for example. We have infinitely many cycles. Periodicity. Period is still 2 pi. Again, 2 pi is the period because that's the width of a cycle. A cycle is the thinnest piece of wallpaper we need, with the property that when you repeat it forever, left and right, we get the whole graph. All right. Oh, and let's notice something else. We have symmetry. What kind of symmetry do we have? We have symmetry about the y-axis. And why is that? Because cosine is what kind of function? It is even. Cosine is an even function. Cosine is even. We have symmetry about the vertical axis, the y-axis. And let's notice something else. Here's y equals cosine of theta. This was y equals sine of theta. You know what? It's the same shape. The sine wave and the cosine wave is the same wave, but they're horizontal translations of one another. That's not so surprising because we're basically tracking the behavior of the x and the y coordinates around this unit circle. It's not so surprising that it's the same basic kind of behavior, but there's like a phase shift, right? Okay. So that's the graph for y equals cosine of theta. It's a horizontal translation for the sine graph. Okay. Now, next time, we're going to talk about domain, range, amplitude, period, translations, various transformations. Next time.